Now, we will discuss the propagation of electromagnetic waves in anisotropic media. In anisotropic media, various interesting phenomena happen, and it is very interesting in the sense that most of the devices that we will be discussing in this course will be around this anisotropic behavior of the medium through which the electromagnetic waves will be traveling. We have seen the isotropic medium where the electric field and the displacement vector they are in the same direction. The other aspects of isotropic medium that also we have seen, in general the propagation characteristics. With that background in mind, we will now look into the various different aspects of the electric field, magnetic field, the displacement vector, their relation, their orientation in this particular discussion. So, the content goes like this. First, we will look at the ED, that is electric field, and the displacement vector, the relationship in a general anisotropic media, and from there we will try to organize the permittivity tensor. In a very special case, the permittivity tensor will correspond to a tensor which will indicate only the principal refractive indices. Then we will make a comparison of the isotropic, inertial and biaxial medium. We will define the various properties of this. Then at the end we will try to bring in the wave equation for anisotropic medium. So, in the case of a general anisotropic medium, in this discussion we will first make these assumptions that the medium is electrically isotropic with electrical permittivity given by this epsilon bar, that is a tensor, but the medium is magnetically isotropic with magnetic permeability mu naught, which is the free space permeability. Okay, so, looking at the ED relationship in anisotropic medium, the constitutive relation in this case is the displacement vector is equal to the epsilon times the electric field vector, which is for isotropic medium this epsilon is a constant, and as a result it is a scalar being, and the D and E are parallel. So, the electric field vector and the displacement vectors will point along the same direction, whereas in the case of anisotropic media this D and E in general are in different directions. Epsilon is a tensor in this case, which is a 3 by 3 9 component tensor, and as we have mentioned that D and E are not parallel as a consequence of this tensor property of the permittivity of this of the anisotropic material. Okay, so, first let us look at the E and D behavior in an anisotropic medium. Let us suppose that the electric field is incident along x axis, so that one can represent the electric field vector as E equal to I cap E x, and there is no y component nor any z component of the electric field. So, the electric field is solely along the x axis. In that case, in general the D is not along x axis, it will be somewhere different from the x axis, and this D vector will be represented by D equal to d x I, d y j and d z k. So, that means there will be 3 components excited because of this incident electric field, which are in general not along the x axis. Similarly, we can apply an electric field in the y direction and as well as in the z direction. But let us see what happens when the electric field is applied along the x axis. So, the d component, because by the very property of the displacement vector, that the displacement vector is proportional to the electric field. So, dx, that is the component of dielectric displacement along the x axis, will be proportional to E x, and this proportionality constant for this particular medium will be represented by epsilon x x, and likewise for dy this will be epsilon y x E x, because this electric field is E x. So, we write in this notation epsilon y x, and similarly for the z component of the displacement, we can write that dz equal to epsilon z x into E x. So, we have been able to decompose the three displacement components arising out of electric field only along the x axis. So, these epsilon x x, epsilon y x and epsilon z x are the permittivity components of the medium when the electric field is incident along the x axis. Next, let us consider the behavior when we apply an electric field along the y axis. In the same way, the displacement vector will be in general not in the direction of the electric field, but in a direction which is different from the direction of the electric field. As a result, in the same way we can write the displacement vector in this case, the x component is equal to epsilon x y E y. For the y component it is epsilon y y E y, and for the z component it is epsilon z y E y. Here also epsilon x y, epsilon y y and epsilon y z are the respective permittivity components when the electric field is applied along the y axis. We have one more case which we will complete the discussion, that is, if the electric field is incident along the z axis. In that case, in the same way, the displacement vector will be in general along a direction which is not along z axis. As a result, in the same way we can decompose the displacement vectors along the three mutually orthogonal axes, where dx will be equal to epsilon x z E z, dy will be equal to epsilon y z E z, and dz will be equal to epsilon z z E z, where again this epsilon x z, y z and z z are the permittivity components in this case. So, now we will arrange all the three electric field vectors to be representing in one arbitrary direction. That is, let us consider that the electric field is now along any general direction, that is E will have three components E x, U y and E z. As a result, the displacement field components will also be represented by dx, dy and dz, but they have a relationship because this dx, dy and dz, all of them will lend its excitation from E x, from E y as well as from E z. So, when we apply an electric field E x, you get E x x E x, epsilon y z, epsilon y x E x and epsilon z x E x. So, these are the three components which are due to the electric field E x. These three components are due to the electric field E y, and these three components are the displacement component which is due to the z component of the electric field. So, these are three simultaneous equations. So, which can be written in the form of a matrix equation, that is dx, dy, dz will be equal to this all the 9 components 3 by 3 matrix E x x, E x y, E x z and so on, multiplied by this E x, E y and E z. In a compact notation, we can write this matrix equation as D equal to epsilon tensor into the electric field. So, this epsilon tensor, as you have seen, is a 3 by 3 permittivity tensor, and this tensor will see that it is symmetric in nature. That means that epsilon x y will be equal to epsilon y x, epsilon y z will be equal to z y and so on, that is epsilon z x will be equal to x z. So, they are symmetric in nature. This component will be equal to this component, this one will be equal to this one, and this one will be equal to this one, and we will find lot of interesting applications using this particular property. So, what we find so far is that the principal in the principal axis system, in general the medium has a set of 3 orthogonal axes, and along these directions D field components follow the direction of the applied field. This is an interesting finding, that if we look for a set of orthogonal coordinate axes within the medium, there is one representing there is one which will correspond to the system, that in which the electric field will follow, the displacement field will follow the electric field in the same direction. That means, when you apply the electric field along the x direction, D will be only along the x direction and so on. Such a set of orthogonal coordinate axes is known as the principal axis system of the medium, and that is the characteristic property of the medium. So, in such a principal axis system, we can write the epsilon permittivity tensor as epsilon x x, epsilon y y and epsilon z z. If we represent with the short notation, then we can write that this is, because there is no other components, no other cross components x y, y z or z x. So, we can write that epsilon tensor as epsilon x, epsilon y and epsilon z. These are the 3 principal dielectric permittivity components of the medium. So, that means, we could find one orthogonal coordinate system, orthogonal axis within the medium, along which the displacement fields will follow the electric field, and if you apply an electric field along the x direction, the displacement will be only along the x axis, and so on and so forth for the y and z component of the displacement vectors when you apply electric field along the x and y direction respectively. So, D and E matrix equation in the case of a principal axis system for the medium can be represented by this equation, that is dx dy dz is now a simple diagonal matrix E x, epsilon x, epsilon y and epsilon z multiplied by E x, E y, E z. So, simply they will relate themselves in this way, that dx is equal to epsilon x, E x, dy equal to epsilon y, E y and so on. So, for an anisotropic medium, there are possibilities that E x and E y and E z may be related in some way or other. For example, if E x, E y, epsilon x, epsilon y and epsilon z, all of them are equal, that means the electromagnetic wave is direction independent, then we call that the medium is an isotropic medium. So, in an isotropic medium, for all directions, whether it is incident along any electric field is incident along any arbitrary direction, or along x direction, or along y direction, or any other direction. So, the displacement vector will follow the direction of the electric field, which is an isotropic medium. But there is another situation where two of them may be equal, but is not equal to the third one. For example, epsilon x is equal to epsilon y, but not equal to epsilon z. In that case, such a medium will be called a uniaxial medium, whereas there is another situation where we will find another group of media where this epsilon x and epsilon y, epsilon z, all three of them are different. In general, such a medium will be called a biaxial medium. That means, in a biaxial medium, the refractive indices or the permittivity seen by the wave will be all different in the all three mutually orthogonal directions. So, the refractive indices we can write in this form that n I is equal to epsilon I epsilon 0, where this is the permittivity and this is the free space permittivity. The ratio and square root of that will represent the refractive index. So, that is along the principal axis. Now, for an isotropic medium, this is in general all of them are equal. So, epsilon x equal to epsilon y equal to epsilon z is equal to epsilon. So, which will be represented by only one epsilon for all the directions. For uniaxial medium, however, there will be one value for which along two directions the refractive indices or the permittivity seen will be identical, whereas this quantity will be different for the third direction. The one along which the refractive index seen by the wave is different is called the extraordinary refractive index, and the wave corresponding to that refractive index will be called the extraordinary wave, whereas the one for which there are two directions for which the refractive indices are the same, the permittivities are the same, we call that is the ordinary refractive index, and the wave corresponding to that refractive index direction will be called the ordinary wave. So, to summarize that the velocity of the waves will be proportional to the refractive indices. This is in general true, and for isotropic medium, therefore, the velocities of the electromagnetic waves will be same in all directions, whereas for uniaxial medium the velocities will be different along two different directions, but for biaxial medium the velocities are different along all the directions. Now, some more facts about the isotropic and anisotropic media. For an isotropic medium, this medium cannot reorient the light, because the light which is incident along a particular direction in such a medium will emerge only along this direction. So, there is no effect, there is no activity of the medium on the travelling electromagnetic waves as regards the direction of propagation. So, the direction of propagation will not be disturbed, will not be influenced by the medium, whereas the situation is different for an anisotropic medium, and this property will be extensively used in the case of various modulators and devices, which we will be discussing later in the later part of this course. So, for an anisotropic medium, the medium can reorient the light, that is the direction of the incident electromagnetic waves can be changed by the anisotropic medium by its property, and also the velocities can also be altered. So, in general such a medium contains one or two special directions, and these directions are called the optic axis, along which they do not reorient the light. So, in an anisotropic medium, particularly in an uniaxial medium, there will be directions along which the electromagnetic waves direction will not be altered, and in the other direction the direction of the electromagnetic waves will be altered. So, to summarize that, a medium with one special direction are called the uniaxial medium. One special direction means the direction along which the direction of the propagation of electromagnetic waves will not be altered. Such one special direction material or the medium are called the uniaxial medium, but for a biaxial medium there will be two such special directions along which biaxial. So, there are two axes, there are two directions along which the electromagnetic waves direction will not be changed compared to or with regard to the direction of the incident electromagnetic waves. So, for isotropic medium, velocity surface will be a spherical, that is, if I imagine the wave front in the all 4 pi solid angle directions, then it will be spherical, because the direction, the velocity is equal in all directions. The examples of such a medium are ordinary glass, garnet and many more. For an anisotropic medium, the velocity surface will be in general an ellipsoid. We will discuss more about this ellipsoid in terms of the index ellipsoid in the later part of this section. So, for an uniaxial medium, the examples are like ice, calcite, quartz, tourmaline, and these are very widely used in designing and in configuring various optical instruments and devices. Biaxial medium examples are mica, topaz, selenite. So, in an anisotropic medium, incident plane polarized light will decompose into two plane polarized light. So, let us suppose that you have an incident plane polarized light, this will emerge out from the medium or within the medium in two mutually orthogonal directions, and in general the two waves travel at different velocities. These are the one which is faster will be called the first waves, and the one which is slower will be the slow waves, and in general because they are travelling with different velocities. So, they will develop a different phase difference, and these phase difference will be utilized to construct devices. Along the two different vibration planes, these two waves will be travelling, and the planes are perpendicular to each other, the vibration planes are perpendicular to each other. There are some more things. So, uniaxial and biaxial media are again subdivided into positive and negative optically active media, depending on the orientation of the first and slow waves. So, in some medium the one which is first waves, in some other medium the same will be referred to as the slow waves. So, this is all relative to the principal axis system of the medium. For quartz, this is a beautiful example which is called a positive crystal. Ne is more than No, that is the extraordinary refractive index is more than ordinary refractive index. So, the typical values are like this 1.5443, 1.5534, and therefore, the velocity of the E ray E wave will be less than the velocity of the O wave. For calcite, which is a negative crystal, the situation is just opposite, that is Ne is less than No, and the typical values are like this. So, you can see that the extraordinary wave travels with a higher velocity than the ordinary wave. So, the velocity or the refractive index is the same along the optic axis for ordinary and extraordinary wave, both they are same. Now, we will look at the plane wave equation solution for this anisotropic medium, and this is the property that we assume that there is no free charge, there is no free current, and B and H they are related by this constitutive relation B equal to mu naught H in such a medium. So, these are the two Maxwell's curl equation from which we can derive, we can organize the wave equation for the anisotropic medium. Fields of plane waves are represented, we have seen that fields of plane waves are represented by E equal to E naught e to the power of I omega t minus k dot r, and similarly for the H field we can represent in this way, where k is the wave vector, and this is the frequency of the electromagnetic waves, and this is the wave refractive indices. We will see that there are two refractive indices, one is the ray refractive index, another is the wave refractive indices. So, if we now use this del del t as to represent this I omega, because this plane wave equation, this is true that if you operate this del del t on this equation, it will just leave I omega multiplied by this E itself. So, we can write the first equation which is which will give you I k cross E. This we have seen earlier, again we will see in details, and I omega b. So, this will give you this equation, and from the other equation we can write that k cross H equal to omega epsilon E, where epsilon in this case, in the case of an anisotropic medium, is a tensor. So, if we organize this equation k cross E equal to minus omega mu H, then you can take k cross E, which will be equal to this quantity, and this actually represents the wave equation, which is purely in terms of the electric field. And in the same way, if we write this equation starting from k cross H equal to omega epsilon E, and we replace E by this by k cross E, then k cross H will be equal to omega square mu epsilon H. So, these two are the wave equations, pair of a set of wave equations which will represent the electromagnetic waves in an anisotropic medium for both the electric field and also for the magnetic field. So, in this section what we have discussed is the relation between the displacement field and the electric field, incident electric field, their connection in terms of the direction and also in terms of the magnitude, which is actually connected by the permittivity values. Then we discuss the permittivity tensor for the anisotropic medium. From there we have seen in a very special situation that for a set of orthogonal coordinate axes characteristic of the medium, we could locate the principal axis system and the values of the permittivity in that principal axis system, that also we have seen. Then we have made a small comparison about the isotropic, uniaxial and biaxial medium. Then we talked about the wave equation in anisotropic medium. In the next section, we will continue with the wave equations in the anisotropic medium, and we will see the various aspects of the waves, the relation of the general propagation vector, the electric field, the displacement vector, the Poynting vector, the magnetic field, all these things will be connected, and we will see how the propagation of the electromagnetic waves gives rise to various phenomena in a general anisotropic medium. Thank you.